So Equilibria 2017, there's not very many questions on Equilibria actually on A2, they mainly appear on AS. So I've found one anyway, let's have a look. It's question number 4, 2017. So we've got an equilibrium reaction, 2 moles of A and 1 mole of B, forming 3 moles of C and 1 mole of D. So once it reaches equilibrium, that's the point when the speed of the forward and backward reactions are equal, and so are the concentrations of each of the reactants and products when they're no longer changing. It says the beaker contained 40 centimetre cubed of 0.16 mole per decimetre cubed aqueous solution of A. So obviously it wants you to work out moles first of all, otherwise it wouldn't have given you concentration and volume. Get the volume into decimetre cubed, so we've got 40 centimetre cubed and decimetre cubed by divided by 1000, 0.04, and concentration is moles divided by volume. So concentration 0.16 is moles divided by 0.04, multiply 0.16 by 0.04, and you come out with 6.4 times 10 to the minus 3 moles of A. I knew I needed to do that because I've been given 2 values for A, so I've got myself a mark straight off. It says, therefore, at the end, I have got, sorry, at the beginning it says that I've got 6.4 times 10 to the minus 3, or 0.0064 moles of A. It says that how much B there is. It tells you how much B there is, 0.0095 or 9.5 times 10 to the minus 3. And it tells you how much C there is as well, 2.8 times 10 to the minus 2. So it tells you how much there is at the beginning. It doesn't tell you anything about D, so we'll have to assume that there isn't any D. It says the equilibrium formed 0.0039 or 3.9 times 10 to the minus 3 moles of A, and it doesn't tell you anything else that's made at the end, so we don't know how much of anything there is at the end. So you need to use molar ratios. So we know how much there was to start with of A, we know how much there is at the end of A, so we subtract the 2, 0.0025 or 2.5 times 10 to the minus 3 moles of A has been used up, and then you've got to use molar ratios. 2 moles of A react with 1 of B, so if I take the 0.0025 and divide by 2, I know how much B is used up, 0.00125, so 0.0025 moles of A is used up, 0.00125 moles of B is used up. If 0.00125 moles of B is used up and I multiply it by 3, 1 mole of B makes 3 moles of C, so 0.00375, that's 0.00125 times 3, that's the number of moles of C, and the amount of D is the same as B, so the amount of B that's used up is the amount of D that's been made, 0.00125 or 1.25 times 10 to the minus 3. Now I need to work out at the end how much there is, so I know how much A I had to start off with, I know how much A I've used up, subtract the 2, 0.0064 take away 0.0025 is 0.0039, I know how much B I started off with, 9.5 times 10 to the minus 3, 0.0095, take away how much has been used up, 1.25 times 10 to the minus 3 or 0.0125, I've got 0.00825 or 8.25 times 10 to the minus 3 B at the end. I know how much C I've got, 0.03175, and I know how much D I've got made, 0.00125. So I'm finished there. Give the expression for the equilibrium constant Kc. So it's the concentrations of C and D multiplied together, divided by the concentrations of A and B on the left multiplied together, raised to the power of the numbers in front. So I've got concentration square brackets of C to the power 3, concentration of D to the power 1, or you don't need the 1 in, divided by concentration of the A squared, because there's 2 in front of the A, concentration of B on the bottom as well, multiplied together to the power of 1. What are the units? Well, I've got 4 units of concentration on the top, I've got 3 on the bottom, so cancel 4 on the top with 3 on the bottom. I end up with 1 concentration on the top. Concentration is measured in moles per decimeter cubed. A different equilibrium mixture of these 4 components at a different temperature contained, oh that's interesting, so a different temperature, so I've got a different equilibrium constant than I had before. Okay, not that that seems to matter very much, but it is a different temperature, so my equilibrium constant Kc has changed. Remember, Kc only changes equilibrium constants, only change with temperature. Nothing else will change them. Calculate the concentration of A in mole per decimeter cubed in this equilibrium mixture. I need to work out what I've got. Oh, it tells me how much I've got at equilibrium. So I've not got to do the at the start, how much is used up, how much is left over at equilibrium anymore. It tells me how much it is. But interestingly, it gives me them in moles. And concentration is moles divided by volume. Now, if I've got equal numbers of moles on the left and equal numbers of moles on the right, I don't need to divide by concentrations, because you'd be dividing by the same divide by volume. You'd be dividing by the same volume, top and bottom. So if you've got equal moles on the top, on the left and on the right, you don't need to divide by volume to change moles into concentration. But I've got 3 moles on the left, 2A and 1B, and I've got 4 moles of product on the right, 3C and 1B. So I haven't got equal numbers of moles left and right. So I do need to convert moles into concentration, because I haven't got equal numbers of moles left and right, and the units of volume are not going to cancel. So I need to work out what my volumes are and do moles divided by volume in decimeter cubed to get them all into concentration. It says I've got 500 centimeter cubed, or 5 times 10 to the power of 2. 500 centimeter cubed divided by 1,000 is 0.5 decimeter cubed. So I take each of the number of moles and divide by 0.5, and I raise them to the powers that are in the expression, and I can work out the missing value. Oh, sorry, actually I've read the question wrong first of all. The temperature, oh sorry, I've got Kc, that's what I was looking for. I've got Kc, I was working out what I've got missing. I haven't got A squared, but I have got Kc. So I've got Kc as 116, but I'm missing A squared on the bottom. So I can rearrange it and introduce 116 for Kc. I can work out what A squared is. A squared 0.0289, so the concentration of A is the square root of that, 0.17. I'm just wondering how many significant figures I put into. Yeah, okay, there's some 3 significant figures, 116, 5.00 times 10 to the power 2, but there are some that are 2 significant figures, 0.21 and 0.076. So I always go to the lower number of significant figures, so I'm going to go to 0.17. Justify the statement that adding more water to the equilibrium mixture in question 4.3 will lower the amount of A in the mixture. This is a tricky one, this is a nasty one. So if I lower the concentrations of everything, Le Chatelier's principle opposes that change, and it tries to raise the concentrations of everything really. But what it will do is it will raise the concentrations by making more moles. So it will shift the equilibrium to the side with more moles as concentrations fall. So it will lower the amount of A by shifting the equilibrium to the side with more moles. So it's trying to increase the concentrations of everything if you lower the concentration. But because there's more moles on the right-hand side, it will try and it will shift it across to the right-hand side because there's more moles there. And if it increases the concentrations of everything, it would increase the concentrations overall if there's more moles on the right hand side. Tricky one, that really. A rare question. I think I've only ever seen that once here before.